In this video, we're going to be using an API to actually get intraday level data for historical option prices. We can actually use this API, ThetaData, to get both historical option prices for end of day, for intraday trades, and even intraday quotes, so bid and ask throughout historical pricing. Now, this amount of data is really unheard of, and that's why I haven't really partnered or had any collaborations with any data providers in this way. Now, this one is one that I highly recommend because of the transparency and the level of data that is available and how quick it is. So without further ado, let's get into it and let's analyze the intraday implied volatility surfaces from a 10 a.m. SPY options contracts and then the 2 o'clock SPY options contract. So I'm importing my dependencies. I've got OS, time, pickle, numpy, pandas, concurrent futures because we're going to thread our responses to the API. We've got matplotlib, we've got date time, time delta, date, and then from ThetaData, which is a Python module, easy to use with the API, we've got the Theta client, option requirement type, option write, date range, and data type. Now, first thing I'm going to do with my call to ThetaData is actually just get all expirations for my SPY options contract. So here I've got a function where I'm creating my ThetaData client. So this is my access for the API. You can see here that I've defined username and password, and I've stored them in my environmental variables. I recommend you guys do the same. I've also got a timeout parameter here. So now that I have the access to the ThetaData client, I'm going to connect to the terminal, and then I'm going to make a request. Now, when I use the get expirations function, and then I call a particular route, and in this I'm going to return the data and get all my expirations for that particular route. My route here is the SPY, so I'm looking for all SPY option contracts expiry dates, and here you can see that all I'm going to do is get the expiration dates that are greater than contracts that are expiring in 7 days time. So I just get the time now. I'm adding time delta of 7 days because I don't really want to get any spurious implied volatility data when I come to calculate implied volatility from Newton-Raphson. So here we've got all the expiry dates that have data on them from September the 14th onwards for the SPY contract. So as you can see, we've actually got 333 options contracts to date, and obviously that's including the historical data. Now, we can get all strikes for each SPY option. So what we're going to do now, we've got defined route ticker and expiration date. So it's a very similar thing. We define our client, we connect to the client, and then we get strikes. So this function, we've got to specify the expiration date of the contract that we're interested in and the route. So here I've just specified the expiry date, September 16th on the SPY futures, and we can just get an example number of strikes back, 283 in total. So then what I'm going to do is I'm going to create a dictionary for all strikes on my SPY contracts that I'm interested in. So remember the expiration date, 7 days time and into the future. I want all the strikes associated with that. So just creating a dictionary of where I'm calling that get strikes function that I've created on the API. Once I've done that, then I can actually find the combined strikes across all these expiration dates. Why is that important? Because sometimes strikes will not be uniform across different expiry contracts. And when I'm trying to create my volatility surface, I'm really trying to get a rectangular matrix if possible. So I'm looking for common strikes across these contracts. And the way that I can do that, I can do the set intersection of all my combined strike lists. So once I've done that, I can find the vol surface strikes that I'm interested in, and I've just printed them out here, and I get something like 30 or so. Now I've just pickled that information down because I didn't want to be gathering that together all the time, and yeah, it's a good habit to get into. So then I can just open that pickle whenever I want, and then I can get the list of my strikes. Now, let's quickly talk about some of the features of the API. So the first functionality I want to show you is retrieving end of day options data. So here's where we can call the get historical function, but my required type, my option required type, is going to be EOD. Now, EOD is just specifying I want end of day. I'm also going to specify a strike, an expiration date, so the specific contract that I'm interested in, and then the date range of which I want the information over. So in this case, I'm just returning the root ticker, the from date, the to date, so just a couple of days over August, the expiration date, the specific strike, and then I'm returning my data frame. And as you can see here, on the right hand side, I've got the data type date and then my volume, close, low, high, and open prices. For retrieving individual trade dates, this is probably the best functionality that I have seen with historical options data. So being able to receive individual trades in an easy to use API like this with a Python module made for it is extremely rare. So here we're using the function get historical option price again, but this time we've got the option requirement type as trade. So now with it as trade, what it'll do by default is it's actually going to return all available trades that were made on that particular trading day. So here I'm just specifying only for August the 31st to the 31st, but if I specified, let's say from the 30th, and then I returned that series, you can see there that I've got double the amount of trades for now 2 trading days. And if I do that again from the 26th, you'll see that will now include the Friday as well historically. So it's, as you can see, it's extremely quick to return so much data back, and I can see the individual trades and the prices that were traded at and the size for all those trades. Now, what we can do is we can use the milliseconds of data to create a date time, and then we can plot this. So I've just done that for 3 days there across the weekend, so you can see that that's a bit messy. If I go back and I just change that to the 31st again, then we'll just get trades for the 31st, and you can see here my date time on the 31st from open all the way through to close. I've got the traded prices. So yeah, very, very handy having individual trades. But more importantly, and what we're going to use today, is the actual quoted intraday option prices. So for this, I'm now going to specify, again, the same function, get hist option, but the requirement type is going to be quote. Now, there is another parameter with this function, and that is interval size. And this is where you can let the API do the work for you. And instead of getting every individual quote that was ever made by change throughout the day or throughout your date range, what you can do is you actually specify a millisecond size to get an average over the ask and the bid for. So I'm just going to set that as a parameter here and make that equal to 0 default for the minute, which is just every time it changes. So if I now do this for the August the 31st, I'm returning back really a lot of rows. So nearly just over 500,000 rows of data here. Now, this is obviously a lot. So if we check that out again for the 31st, and just to show you how quick that kind of updates as I'm speaking here, it's lightning quick, and you can obviously change the strike if this strike exists. I think so. So obviously for any strike within this data, we've got over 1 million rows of data coming back for this strike. So obviously the market maker was a little bit more active on this particular day on that strike than further out of the money. So now that we've got that, what we're actually going to do, because these aren't uniform with the number of quotes, I am going to use that interval size, and I'm going to get back the average bid-ask quotes on a 5-minute basis. So to do that, I do it in milliseconds, so 5 times 60,000 for a minute. So 5 minutes, and I'm going to pass that through to my function quotes, and then I'm going to change, I'm going to create a column called date time. So that's just where I'm going to take that millisecond column and then add that to the date. So if we do that, I will return now my pandas data frame, but for every 5 minutes throughout the day. And you'll notice that it starts from midnight and it goes all the way through to midnight. That's okay. It just for those, this is going to be the closing prices and these are going to be before open. So what we're actually interested in is the time 10 a.m. and 2 o'clock. So I'm going to find those indices within this number of rows throughout the day, and then I've determined that the 10 o'clock one is 120 and then the 1400 is 168. So if we want to look at what the afternoon data looks like for the period starting 1400 to 1405, then I've got the bid size, the bid condition, the bid exchange, ask size, ask condition, ask and ask exchange, and of course the date. So given that amount of data, what do I actually want back? Well, I want some kind of weighted mid-price. So this is going to give me a little bit more flavor on if there is an imbalance between the size offered on the ask versus the bid. This approach, also known as the micro price, is more or less a weighted mid-price. So I'm going to use this for this weighted mid-price for our calculation of implied volatility. So I've created a pandas function where I take in a row and I calculate this for each individual row. So we're going to get the mid prices for each of these rows, and we're going to calculate the mid price. Now I'm obviously only interested in 10 o'clock and 14 o'clock, 1400, where I can just apply these indices and get those values back. So I'm going to create a request now with that function between 10 and 1400 for the weighted mid price, just using our quotation function, and then just subsectioning further to only return a tuple of our mid price for the morning and our mid price for the afternoon. And this is now a function that we can call for a particular strike for a particular expiry. Now, the reason that I've done that is because I want to multi-thread my responses to ThetaData API. Every time I send a response, I'm going to process it through one thread on my computer. So we're actually going to explore using current futures module to actually perform multi-threading and processing of the responses of ThetaData API. So we need to create a function that we can call with our specific parameters of interest. So these are the root ticker, the expiry date, the strike, from and to date, and the interval size, 5 minutes. So we need to know the maximum number of threads our computer has. Mine has 8, not so good, but look, we'll live with it. So you specify this, and then you specify your parameters of interest, and I'm just going to run through a dictionary of expiry dates, and then I'm going to create my executor, which is current futures thread pool executor with 8 threads, and then I'm going to have a list comprehension of my executor.submit with my function and then variables that I want to pass for each individual parameter set. And the only parameter I'm changing here is actually the strike, because each time I go through this higher level for loop, I'm changing the expiration date here. So I'm only changing the strikes within this execution here. Then I'm going to wait for my futures, my list to finish, and then I'm going to move through the for loop. Now, you can execute this, but as you can see, I've printed out the time, and I've just tried to specify where there's data and where there's not. But as you can see, it's very comprehensive for the quote data. I've been able to get data for all these strikes, for all these expiration dates, and you can see each expiration date has taken me about 13 seconds, 10 seconds, to return the data. So it has been extremely quick. Like always, I encourage you to go ahead and make up your own mind and test out ThetaData for yourself. So save down with pickle. So I'm just going to save that data by pickling it. So I've got datas, and then I can open it up anytime. Now, the way I need to process this now, remember I had a tuple of the mid prices in the morning, mid prices in the afternoon, and I want to separate those into 2 numpy arrays. One called the morning, the price morn array, and the one called the price arvo array. I'm very good with naming variables, as you can see. So what I can do is I can then just subsection this with a list comprehension. If a value doesn't exist for that particular time period, then it's just going to return an NA. So that's fine. I build up my list for our price morning array and price afternoon array, and you can see the dimensions here. Now, creating data frames for the option maturity, strike, and prices. So here I'm going to, if you haven't done so already, I encourage you to install pyvolib vectorized. We're going to need it for calculating the implied vol soon. And then for Scipy interpolate, we're going to import grid data. So now our maturities is going to be a numpy array from the expiration date minus the time now in days divided by 365.25. And this is for all expiration dates. Now the strikes are just going to be our vol surface strikes that we calculated as the combined strikes across all those expiries before. Now the vol surface morn and the vol surface arvo are just the names of the actual data frames that we're creating with these two arrays. Then I'm actually melting them, which means just simplifying them in terms of a row per data each. So really elongating these pandas data frames so that each row represents a maturity, a strike, and a price for a particular option. So we have this for the morning and the afternoon. I define those columns, and then I need to create a mesh grid. Now the mesh grid's important because this is what we're actually going to be able to do to create our interpolated surface. So we need the strikes and the maturity dimensionality placed in our mesh grid, and then we're just going to return that mesh grid as S for strikes and M for maturity. I'm just going to check the dimensionality lines up with our price morning array. So our shape of S and our shape of M is actually equivalent to our price morning array now. And what does that look like? Well, you can take a look at the data and subsection it as you wish. And I've just shown you what an output looks like at the moment. Now, the first thing we're going to do, we're going to interpolate the price surfaces. So using Scipy grid data, we can interpolate our multivariate price array and return a mesh for plotting. So here I've just defined my parameters in our mesh grid. I'm using grid data to get the mesh grid for both the morning and the afternoon just on the prices, and I'm checking to make sure that there is no NAs. If there's not, then we can use grid data. So I'm just removing all the positions that actually contain NAs. Now I build up those pandas data frame, and if we just look at our morning prices first, you can see, so at 10 o'clock, you can see here on the left-hand side, I've got our SPY option prices, here our strikes, and here the years to maturity. And Plotly is pretty good because you can move around the graph like this. So those markers in red are the market prices, and blue is my interpolated grid data surface. So looking pretty good so far, but remember these are prices, and what I actually want is the implied volatility. Now, just plotting both the morning and the afternoon, you can see the afternoon surface is in red and the blue is the morning surface. So not too much difference in terms of prices, a little bit, but we'll see how that actually contributes in terms of implied volatility, and I think we'll see some differences there. Now, calculation of the volatility surface. This is important. So here we're really using a Newton-Raphson method from our pyvolib vectorized module. So what you can do, you actually need to specify the price of the underlying at those particular times. I've gone through and used a different reference here. For indices, ThetaData doesn't currently have the underlying here, so it can't return the Greeks, but for all other options, it does return the higher order Greeks for you, and I'm going to be demonstrating that in another video. So that's pretty impressive. But for today, I'm going to specify the price in the morning at 10 o'clock and then the afternoon at 2 o'clock. And these are the values. You'll have to take my word for it. So here is the mesh grid that I'm creating, and then I'm using implied volatility from our pyvolib vectorized library, and I'm specifying the strikes and then the maturities and then the price in the afternoon and then the price in the morning. So once you've specified those parameters, you'll be able to execute these two functions, and then you can do a bit of manipulation on the data. For example, I don't want to get spurious results for my volatility. So if the volatility returned less than 1 or greater than 120% volatility, I'm just going to return an NA. I don't want to plot it. But yeah, look, you could do better filtering out functions than that to really analyze your data. I'm then just creating, I'm adding to our pre-existing data frames this information, and then I'm going to interpolate using a spline. The type of spline I'm going to use is the bivariate spline, smooth bivariate spline from Scipy. So for interpolation of this information, all we need to do is we need to flatten all our arrays. We need to create masks for where the NAs exist, remove them, and this is important because obviously you can have NAs in functions that are in different spaces within these arrays between the morning and the arvo. There might be data that didn't exist in the morning that does exist in the afternoon, so you need to be careful with NAs when using the Scipy's interpolate smooth bivariate spline. So you remove all the points in the array where there are NAs, and then you really use the interpolate smooth bivariate spline with all our parameters that we've defined. Now here I've just defined a spline order arbitrary for 4 and 4 in both directions, but again, you could specify and tinker around with whatever fit you want, and then use some kind of metric like we have in our volatility video for assigning parsonomy in terms of fit with your data. So I'll leave that with you, but this is really for demonstration of the capability. Now let's go through, and we've got our interpolated surface now that we've actually created values with. So now we've got our secondary mesh. So just our mesh that we're interested in. I've just gone, okay, I want to get from my lowest strike to the highest strike and lowest maturity to the highest maturity. And I want to take 20 even steps in between them. So using the linspace function there in NumPy. And then I'm going to actually pass that through mesh grid so I can get my equivalent size array for our strikes and our maturity. And I'm going to pass in the tuples to our interpolated smooth bivariate spline surface. I'll then have 2 arrays where I've got our morning and afternoon volatility interpolated, and then I can plot this information. And the first one, I'm just going to look at the volatility surface of the morning, and you can see here our data in red is our actual volatility data. So our blue surface is our spline fit that we've actually done. So there you can see that it's a smooth fit. And if we actually compare the morning and the afternoon volatility splits, what we get is 2 curved functions that look like this. And you can see in the morning that's blue, and then in the afternoon that's red. And here you can see there's definitely less implied volatility on those contracts in the afternoon compared to at open when the contracts are heavily bid up, etc. So it's very interesting to visually look at the differences in the option implied volatility of these mid prices, but obviously you could do any number of different pieces of analysis looking between correlation intraday, and it's pretty impressive that this API allows you to look at all quotations across a really diverse range of contracts and be able to actually get this level of information in a really quick and easy to use way with the Python API. Now, obviously, I do have an affiliate relationship with ThetaData, and I am showing this as a sponsored segment of this program. But I would say that I don't do this often, and really this API is something that I'm going to be using now and have a collaboration with for a long time. And this is because I truly believe in the product, and there aren't many opportunities to actually get intraday trade data and intraday quotation data, especially for historical option pricing. So I would recommend anyone who is looking for option prices historically like this and wants to explore the capability and be able to look at higher order Greeks and get them back, and yeah, even just the data that we've seen today, please go ahead and take a look at the website, ThetaData. I have a link in the description, so if you're interested in looking at ThetaData more for your own analysis, please go ahead and look at the link in the description. Thank you very much, and until next time, YouTube, see you later.